Hi, in today's video, we'll be continuing on the introduction into discrete mathematics, following what we have said earlier about logic and propositions. So now, we'll move on to quantified statements. Quantified statements are statements because your original statement was not able to capture the full meaning of the statement. What do I mean? For example, we want to know whether our set that we are talking about have a certain property, and that means that every element in X is odd, for example. Then how do we write them notation is X1 is odd or not, X2, and then we continue. But we can see that there's this ... notation, which is very informal, and so mathematicians came up with a way to express this ... in a different way. And symbolically, we write this inverted A, which represents for all X in the domain. And if we want something to be an OR that goes on forever, then there exists an X in the domain. You can think about it, but it should come rather intuitive why this is so. And so, this for all is known as the universal quantifier, and the there exists is known as the accidental quantifier. Take for example, this statement: for every X, which is an integer, 2n is even, and it can be expressed as for all X element of the integer set, 2n is even. So this is the basic idea of what are quantifiers, and we can manipulate them like how we do with normal propositions by putting multiple quantifiers in a statement. So one example would be for all X reals there exists a number such that the cube of it is X. And this statement is true regardless of what X is. But now, if you were to reverse an order of the quantifiers and express that there exists a Y such that all the X's equals to this cube, then it is false, because X is 1, Y is 1. But if X is 8, Y is 2. And so there is no one particular Y that satisfies this condition. And this makes us understand that we need to be cautious and be aware of the order of the quantifiers so that we do not prove the wrong statement. Next, let's see how do we want to negate quantified statements. Imagine I say that for all X, X is even. That means that if I take any of the X that I want, for example any of the integers, I can find I'm saying that everyone is even. And so if we want to negate this statement, it means we must find a particular counterexample to show that this statement is false in order for this whole statement to be false. And so, when you write it out in English, it's for all X, Px. Negating it, it will mean that there exists a particular X such that Px does not hold. And symbolically, we can just express it as for all X in the domain, there exists an X in the domain such that Px does not hold. Let's take this concrete example over here. It says that for all real numbers, the square of it is non-negative. Negating it would mean that we find a real number such that the square of it is negative. And obviously only one of these statements is correct and the other will be false. So this gives you an idea on how to deal with quantified statements. And we'll move on now to having more examples of a conditional statement. In this case, we'll learn how to negate conditional statements. We understand what does P implies Q mean. It means if P is true, Q is true. And so, how do we make this false? The negation of this must be something to counter example. It's a counter example to this statement of P implies Q. And so, the negation of it has to be when P is true and Q is false. And this gives us the chance to write P and not Q. So you can think about it. So if P is true, Q true, this statement is true. But if here is P is true, Q is true, not Q will be false. And so the overall statement will be false. And you can actually just use the truth table to verify that these two statements are now logically equivalent. But I hope that learning how to negate the quantified statement where I think of a counterexample allows me to understand how to negate more complicated statements on the go, where you just need to imagine that you have a counterexample to this original statement so that it is the negation of the statement. Lastly, I'll go through what are logical inference. It's actually a step-by-step process to help you determine whether the statement you want is true or false. We have seen how we have used logical equivalence in normal statements where we shown that conditional statement is true or otherwise. But knowing whether this conditional statement is true does not tell us whether P or Q is true. But having another information such as P is true would imply that Q is true, or imply that you are able to determine the true value of Q. And so this is what it means by logical inference, where you're given statements to infer whether the third statement has a true or false value. The earlier rule that I've said is called modus ponens, and there are many other rules that's available for your checking using truth tables. Many of these rules were developed via our common knowledge and everyday inferences, and so you might find them very, very intuitive. But it is clear that in mathematics, intuition does not lead to proof, and so proving stuff will be later on in another video. But for this video, you get to touch base with how you should use this logical inference to determine the truth value of a statement. Let's take more examples to practice. For example, if I know P and Q already, then I will know the truth value of P and Q. And if I know the truth value of P and Q being true, it will force P to be true, or it will force Q to be true as well. Lastly, if I know P is true, then P or Q must be true, because as long as one of them is true, the whole expression will be true. And so, you'll see how we applied these various forms of logical inference. That's all for the part about logic and propositions. This will be part of a series that will be covering more about discrete mathematics. The next chapter on counting, you can find them in other videos that I've done. Thank you for listening, and I hope you have enjoyed it.